Good morning everyone. So, we will be looking into the modeling of unstarred batch experiments, now unstarred batch membrane based separation processes, and in the last class we have elaborated what is the importance of these unstarred batch experiments and why we would like to model them and how we can generate a large number of data in a short period of time. So, what we did, we wrote down the concentration species balance equation within the mass transfer boundary layer, and in this case the concentration is a function of time as well as space in the y direction. Okay. So, we reduce the equations into and analyze the equations and found out that a similarity solution can be useful in this case, because the governing equation is a parabolic partial differential equation and one of the boundary condition is residing at infinity. So, in this case we can have a similarity solution like the cross flow experiment, and we can we made the equation non-dimensional and we formulated the boundary conditions as well and made them non-dimensional. Then what we did an order of magnitude analysis at the edge of the concentration boundary layer and found the similarity parameter in this particular case. And in this class we will be getting the, so what is the next procedure? Next procedure is replacing the partial derivative in terms of derivative of similarity parameter, and we expect the partial differential equation will now reduce to the ordinary differential equation, and we will look into the solution of the resultant ordinary differential equation. So, if you remember the governing equation that we have written in the last class for the transient or the time varying filtration system is del C star del tau is equal to minus j minus p e w del C star del y star is equal to del square C star del y star square, and we wrote down the initial and the boundary condition at time tau is equal to 0, that is the initial condition, C star is equal to 1, that is C is equal to C naught, at y star is equal to 0 you have the mixed boundary condition, that is the convective flux towards the membrane and the diffusive flux away from the membrane will be equal. Okay. Del C star del y star plus P E W C m star times real retention is equal to 0, and at y star is equal to infinity we had C star is equal to 1, right. Now, this boundary condition gives the initial condition, this is the boundary condition at y star equal to 0, and this is the another boundary condition at y star is equal to infinity, considering the mass transfer boundary layer is really very small, order of magnitude or less compared to the actual dimension of the system. So, it is in fact on the order of 10 to the power minus 6 meter. Okay. Now, this governing equation is a parabolic partial differential equation and this boundary condition is at infinity. So, we can have a similarity solution, and indeed we can have a similarity solution. We have analyzed the situation and found out the similarity parameter in this case as y by delta, which is nothing but y star, make it non-dimensional. So, it becomes y star by root over tau. Okay. So, this is the similarity parameter we have derived in the last class. So, what is left now? The left is basically to get the derivative of this partial derivative of the original in terms of the original coordinate system to be expressed in terms of the similarity parameter or combined variable parameter eta. So, it will, instead of two independent variables y star and tau, you will be having a single variable eta, and the resultant equation will be boiled down into an ordinary differential equation. So, let us look into this derivative. So, del C star del tau will be nothing but del d C star d eta times d eta del tau. So, this becomes d C star d eta, and del eta del tau will be y star will be remaining as it is, tau to the power minus half, right. So, it will be minus half to tau to the power minus 3 by 2. So, it will be nothing but tau root over tau. Okay. Now, this becomes y star by root over tau, this becomes nothing but eta. So, this becomes eta minus eta by 2 d C star d eta, and you will be having another tau here. So, it will be you will be having eta by 2 tau dc star d eta. Okay. So, this partial derivative with respect to tau can be expressed in terms of the total derivative with respect to eta. Now, we will look into the other derivatives del c star del y star and del square c star del y star square. So, del c star del y star will be del c star del eta del y star, and if you remember, eta is nothing but y star by root over tau. So, therefore, del eta del y star will be nothing but 1 over root over tau, and c star is now supposed to be a sole function of eta. So, this partial derivative will be replaced by a total derivative now, dc star d eta. And what is del square c star del y star square? Del square c star del y star will be nothing but del y star times del c star del y star, right. Now, I replace del y star by del eta del y star, del c star del y star remains same, this becomes del eta del y star using the chain rule of the differentiation. And what is this del c star del y star? It is already expressed in terms of dc d eta. So, this becomes d d eta, this becomes total derivative because concentration is now a sole function of eta. So, this will be root over tau dc star d eta, and del eta del y star will be again 1 by root over tau. So, this becomes 1 over tau d square c star d eta square. So, that way we can express all the partial derivatives in terms of the single variable eta. Now, you can substitute in the governing equation, this becomes what? So, you just write it del c star del eta becomes minus eta by 2 tau dc star d eta minus pw del c star del y star becomes 1 over root tau dc star d eta 1 over root over tau dc star d eta, and this becomes d square del square c star del y star square will becomes 1 over tau d square c star d eta square. So, multiply both side by tau and let us see what you get. This becomes minus eta by 2 dc star d eta minus pw root over tau dc star d eta is equal to d square c star d eta square. Now, we can combine these two terms, and this ordinary differential second order ordinary differential equation can be written in a neat form, and that becomes this d square c star d eta square is equal to minus eta by 2 plus pw root over tau dc star d eta. Okay. So, the governing equation becomes a second order ordinary differential equation. Now, this now if you remember the permeate flux, that is the permeate flux that you are getting out of the membrane will be pretty small, and these will be and the thickness of the concentration boundary will be also very thin compared to the any physical dimension of the system. So, therefore, we assume that the y component velocity in the concentration boundary layer will be same as that is valid at the wall, although it is an approximation, but it will be a valid approximation there. That means, V within the mass transfer boundary layer will be nothing but approximated as minus j. So, therefore, and we have seen that this value of the permeate flux or the solvent flux will be inversely proportional to the thickness of this delta. Less be the thickness of the concentration boundary layer, more less resistance it will be offering to against the solvent flux. So, you can expect a higher permeate flux at the beginning of the at lower period of time. Now, in this case delta will be function of tau time. So, when the thickness becomes more, the permeate flux will be small. So, it is inversely proportional to that. So, therefore, non-dimensional permeate flux will be inversely proportional to delta star, okay. And delta star is directly proportional to root over tau, that we have already seen, because the definition, if you look into the definition of eta, eta is nothing but y star by del star, and del star is inversely del star is proportional to t to tau to the power half. So, it will be 1 by root over tau. So, delta star is directly proportional to root over tau, and therefore, P w will be nothing but it is inversely proportional to root over tau. That means, P w times root over tau is a constant. And we call this constant as A. Okay. So, in terms of this new constant, now we can rewrite our governing equation as d square c star d eta square is equal to minus eta by 2 plus A d c star d eta. Now, we have to solve this equation. At the same time, we have to write down the boundary conditions in terms of eta as well. Now, since this is a second order ordinary differential equation with respect to eta, we must be having two boundary conditions on eta to solve this governing ordinary differential equation. So, at eta at y star is equal to infinity, c was is equal to c naught. So, or c star is equal to 1. Okay. So, therefore, and at eta is equal to infinity, we have c star is equal to 1. That is one boundary condition expressed in terms of eta, and the other boundary condition was at eta is equal to 0. At eta is equal to 0, you had d c star d eta plus a c m star r r is equal to 0. How did you get this equation? This equation can be obtained if you look into the governing equation, the original governing equation at eta equal to 0. That means, let me clarify everything, and let us do a couple of steps derivation. So, that will be, then things will be clearer. At y star is equal to 0, we had the original boundary condition was as del c star del y star plus p w c m star r r equal to 0. That was the original boundary condition. Now, if we express del c star del y star in terms of eta, we have already derived that 1 over root over tau d c star d eta, right. Del c star del y star can be written as 1 over root over tau d c star d eta. We have already looked into the derivation, p w c m star r r is equal to 0. So, d c star d eta plus p w root over tau c m star r r is equal to 0, and this is the constant A that we have already defined earlier. So, we get this expression, which is the boundary condition at eta is equal to 0. Y star equal to 0 means eta equal to 0. So, that is how you obtain the boundary this boundary condition in terms of eta, and these two boundary conditions, this is number 1, this is number 2, okay, that defines the solution of the governing equation, that whatever we have expressed earlier in terms of eta. So, this gives the derivation of the how you obtain this boundary condition at eta is equal to 0. Okay. Now, you will be in a position to get the solution of concentration profile. So, let us write down the governing equation one more time, d square c star d eta square minus eta by 2 plus a d c star d eta. Now, you consider d c star d eta is another variable z. Okay. So, this becomes dz d eta minus eta by 2 plus a times z. So, this becomes dz by z is equal to minus eta by 2 plus a d eta. So, the one first integration will give you ln z, right. So, in terms of the after first integration, what you get is you get z is equal to k 1 exponential minus eta square by 4 minus a eta. Okay. So, k 1 is the first constant of integration. Okay. So, what is z? Z is nothing but d c star d eta. So, one more integration will result you the expression of sister as a function of eta. What is the expression of sister? Sister will be k1 exponential minus eta square by 4 minus a eta d eta plus k2. And what is this integration? Integration is basically over the variable eta. So, and the minimum value of eta is eta equal to 0, and so this integration basically runs from 0 to eta implicitly. Okay. Now, you have the two boundary conditions that we have just discussed in the last slide, and using these two boundary conditions one can evaluate these two constants of integration. Okay. Now, let us look into the boundary conditions and evaluate the constants of integration k1 and k2. Okay. The first constant boundary condition was at eta is equal to infinity, sister is equal to 1. That means 1, you just put this condition in your solution, 1 becomes k1 0 to infinity exponential minus eta square by 4 minus a eta d eta plus k2. Okay. Now, again, if you know the value of a, then this integral is known to you because it is a definite integral, and once you know the value of a, because that is a constant, it must be assuming some value, and how to evaluate the value, that we will see later on. Once you know the value of a, then you can this definite integral can be evaluated by using any trapezoidal's rule or Simpson's rule, putting the upper limit as some higher numbers, maybe 10, 15 something. And how to decide 10, 15, I think we have discussed earlier. Just put any number and you will be getting a result. That just change the number, just increase the number arbitrarily, let us say from 10 to 12, and change and look into the result. If the result does not change in the decimal third or fourth decimal place, that means 10 is good enough as infinity for this particular problem. Okay. So, let us indicate this integral as I. So, this becomes k1 I plus k2. This is equation number 1. Then we put the other boundary condition. The other boundary condition was at eta is equal to 0, you had dc star d eta plus a cm star rr is equal to 0. And what is dc star d eta? Dc star d eta is nothing but z, the variable z you have defined, z evaluated at eta is equal to 0 plus a cm star rr equal to 0. Now, let us look into what is z at eta is equal to 0. If you look into the expression of z, the expression of z was k1 exponential minus eta square by 4 minus a eta. So, therefore, z evaluated at eta equal to 0 is nothing but k1. This exponential term becomes 1. So, z at eta is equal to 0 is nothing but k1. And what is cm star? If you look into the expression of sister, that was k1 I, k1 0 to eta exponential minus eta square by 4 minus a eta d eta plus k2, right. And what is cm star? Cm star is nothing but sister evaluated at y star equal to 0, and y star equal to 0 is nothing but eta equal to 0. So, cm star is nothing but sister evaluated at eta equal to 0, and once it is eta equal to 0, that means this upper limit becomes 0. So, this integral will be then from 0 to 0. So, whole integral will vanish. So, this is nothing but the other constant k2. Okay. So, once you get that, then you can write the boundary condition of at eta equal to 0 at dc star d eta at eta equal to 0 is nothing but k1. So, this will be k1 plus a, cm star will be nothing but k2 rr equal to 0. So, you will be getting the second equation from the second boundary conditions. Now, there are two equations and two unknowns k1 and k2 to be evaluated. Once these two constants are evaluated, then you will be getting the full concentration profile within the mass transfer boundary layer. Now, in the next slide, we will be doing the derivation of k1 and k2 from these two equations. Okay. So, from equation 2, we will be getting k1 is nothing but minus a k2 rr. So, you just put it into the first equation, that will be k1 I plus K2 is equal to 1. So, K1 is minus A K2 RRI plus K2 is equal to 1. So, therefore, K2 will be nothing but 1 by 1 minus A RRI. So, this is the expression of K2, and what is K1? K1 is nothing but minus of A RR divided by 1 minus A RRI. So, this is the expression of K1. Okay. So, using these two constants K1 and K2 and knowing the value of A, one can evaluate the concentration profile within the mass transfer boundary layer. Now, but our aim is to basically evaluate what is the permeate flux, that is non-dimensional permeate flux, and what is the permeate concentration, Cp star. And Cp star can be obtained if you can evaluate the Cm star, the membrane surface concentration, through the relationship Cp star is nothing but Cm star times 1 minus real retention. If you know the value of real retention, that can be, in fact, there are several ways to evaluate the value of real retention of a particular membrane solute system from various independent set of experiments that we have discussed already earlier. So, once you know the Cm star and PW, from this expression you can calculate the permeate concentration as well. So, you can predict the system performance at every location of time point. Okay. So, we have to evaluate the concentration profile at eta is equal to 0, that is the Cm star. What is the expression of Cm star? Now, if you look into the derivation earlier, Cm star was nothing but the constant K2. So, we write down the Cm star is nothing but constant K2 is equal to 1 over 1 minus A RRI. Okay. And we have the Darcy's law will be valid as the solvent flux equation through the porous medium for every point of time, and if you remember, the non-dimensional form of Darcy's law will be Pw tau B into 1 minus delta pi divided by delta P. How you obtain this equation? This equation obtained by the non-dimensionalization of the Darcy's law. If you forget, I can do a couple of steps and you can rebrush your memory that Darcy's law was nothing but J is equal to Lp del P minus del pi, and you just make it non-dimensional, J d by d. In this case, d equivalent will be nothing but the radius of the cell, because it is the unstarred batch cell. So, it is a cylindrical cell with the inner radius is r, let us say. So, Lp r by d, make it non-dimensional. So, therefore, take delta p out. Okay. So, take delta p out, this becomes delta pi by delta p. Okay. So, what is J r by d? This is nothing but Pw, non-dimensional Pw. This is valid at every tau, and Lp r del p by d is a constant b, and this is 1 minus del pi by del p. This is a non-dimensional parameter that takes care of operating pressure, diffusivity, solute property, operating conditions, membrane property, okay, and of course, the geometry property R. So, and what is delta pi? If you remember, pi is nothing but, we had an expression, pi is equal to nothing but AC A1 C plus A2 C square plus A3 C cube. So, we have the expression of pi as a polynomial of concentration. So, what is delta pi? Delta pi is nothing but the osmotic pressure difference between the membrane surface and in the upstream and the permeate stream. So, delta pi will be nothing but A1 Cm minus Cp plus A2 Cm square minus Cp square plus A3 Cm cube minus Cp cube. Okay. So, now you can omit, you can replace Cp in favor of Cm by doing this exercise. Cp is nothing but Cm into 1 minus real retention. If you substitute this, delta pi will become a sole function of membrane surface concentration. So, let us do that and see what we get. What we will be getting is that delta pi will be nothing but A1 Cm RR plus A2 Cm square, this becomes 1 minus RR square, this becomes A3 Cm cube 1 minus RR whole cube. Okay. and now make Cm non-dimensional in favor of the bulk concentration. So, this becomes A1 C naught RR times Cm star, this becomes A2 C naught square 1 minus RR square times Cm star square plus A3 C naught cube 1 minus RR whole cube Cm star cube, and this becomes B1 times Cm star plus B2 times Cm star square plus B3 times Cm star cube, and your B1 will be nothing but A1 C naught RR, your B2 will be nothing but A2 C naught square 1 minus RR whole square, and B3 will be nothing but A3 C naught cube 1 minus RR whole cube. So, this is a convenient way of to express delta pi in terms of Cm star only, and 1 by delta pi by delta p will be nothing but B1 by delta p plus delta p Cm star plus B2 by delta p Cm star square plus B3 by delta p times Cm star cube. And now this becomes a non-dimensional number, this becomes a non-dimensional number, this becomes a non-dimensional number, and all the variables are non-dimensional. So, whole thing becomes non-dimensional, and in a sense your osmotic pressure difference can be expressed in terms of Cm star only, and that is the way how the derivation goes. So, what you have now? So, let us write down the governing equations, whatever you have the relevant equations in one place, that will be better, otherwise the whole thing becomes cluttered. Okay. So, the relevant equations are, first equation is Cm star as 1 minus A RR I, and what is A? A becomes, A is nothing but, if you remember, A is nothing but Pw root over tau. Okay. And what is the Darcy's law? Darcy's law is nothing but Pw at any point of time becomes B times 1 minus delta pi by delta p. Okay. And this is a function, sole function of Cm star. Okay. So, that is it. Now, using an appropriate algorithm, one can do an iterative calculation and can get the permeate flux and permeate concentration at every time point, and you will be getting a profile as a function of time. How? So, we use the following iterative algorithm. What is the iterative algorithm? At a particular operating time, let us say 5 second, 10 second, whatever particular time tau, you do the following. Step number 1, guess the value of Cm star. Okay, guess the value of Cm star. Once you guess the value of Cm star, and you can, once you guess the value of Cm star, you can calculate Pw from equation number 3. What is equation number 3? From here, this let us say 3, 2, 1. Okay. So, you know the value of Cm star because you have already guessed it, and this is a sole function of Cm star. Delta P is the operating pressure, operating condition that is known to you because you are setting it. B is a parameter that is all the values are known to you. Okay, LP, membrane cell radius, so on and so forth. So, you can get the value of Pw. Once you know the value of Pw, from step number 3 is from equation 2, you know the time point, you know the value of tau, you know the Pw. So, you can get the value of A. So, okay. So, evaluate A from equation 2. Once you do that, then you are in a position, once you know the value of A, you are in a position to evaluate the definite integral I. Evaluate I from its definition, I is equal to 0 to infinity exponential minus eta square by 4 minus A eta d eta. Okay. So, you know the value of A. substitute there. So, everything is known, eta is the dummy variable. So, just evaluate the definite integral I. Okay. So, once you know the value of I, then you can go back to equation number 1, because I is now known to you, A is now known to you, R you have already determined. So, you can calculate Cm star from equation 1 and check whether this calculated value is close to the guess value or not. So, next one is just iterate on the absolute value of Cm star guess minus Cm star calculated is less than epsilon or not. If not, then you guess a new value of Cm star. Likewise, this loop has to be iterated for a particular time point. And what you do next? Next, you have an increment of time tau, let us say tau plus delta tau, and reiterate this equation, these steps. But in the second step, you should have a judicial guess of Cm star. The judicial guess is basically the converged value of Cm star at the earlier time point. Then it will be the iteration or the convergence will be faster for the next time point. Likewise, likewise it will be continued. Okay, it will be continued. And what is the final outcome of this exercise? Final outcome is that you will be getting a profile of Cm star as a function of tau, you will be getting a profile of Pw as a function of tau, right. So, out of it you will be getting Pw as a function of tau, and this is Pw and this is Cm star as a function of tau. Once you know the Cm star as a function of tau, you can get a value of Cp star as a function of tau through the relationship Cp star is equal to Cm star into 1 minus real retention. Okay. So, this way one can get the one can predict the system performance as a function of time in an unstarred batch cell experiment. And why you are conducting the unstarred batch cell experiment, that I think we have discussed that issue earlier, and that is the way. Now, one may be, being a chemical engineer, you may be interested what is the expression of mass transfer coefficient in this case. Now this mass transfer coefficient K is a vital parameter as far as the design of any chemical engineering system is concerned, where the mass transfer is involved. So, we start with the definition of mass transfer coefficient. K times Cm, that means C at y equal to 0 minus C naught is equal to minus d dc dy del c del y at y is equal to 0. That is the definition of the mass transfer coefficient. Now, what we will do, I think we have done this exercise earlier in the case of rectangular geometry. We have to replace del c del y in terms of dc star d eta, okay, in terms of non-dimensional similarity parameter eta, and before that you have to make this equation non-dimensional. So, first we make the equation non-dimensional, then we put the value of the governing the derivative in terms of eta. So, K Cm star minus C naught is equal to minus d del c star del y del c del y, okay, there is no star here, at y is equal to 0. Now, you divide both sides by C naught. So, this becomes Cm star minus 1 is equal to minus d del c by C naught. So, it becomes del c star del y at y is equal to 0. Okay. Make y star as y by r. So, y is nothing but r times y star. So, K Cm star minus 1 minus d by r del c star del y star. Now, this becomes y star is equal to 0, and what is this? K r by d is nothing but minus del c star del y star at y star is equal to 0 divided by c m star minus 1, and this quantity k r by d is nothing but the Sherwood number. Now, there is a neat expression of Sherwood number in terms of non-dimensional parameter, and if you now put the expression of del c star del y star in terms of eta, and this becomes Sherwood is equal to minus 1 over root over tau dc star d eta at eta is equal to 0 divided by Cm star minus 1. Now, we have done this exercise earlier just a few minutes back, the dc star d eta at eta equal to 0 and Cm star in terms of the integration constants, and this becomes minus k1 by root over tau divided by k2 minus 1. Okay. Just put the value of dc star d eta at eta equal to 0. We have done that probably a few minutes back, and Cm star is nothing but k2. So, it becomes k2 minus 1. Now, you put the expression of k1 and k2, because you have evaluated the k1 and k2 in terms of a, rr and I, and substitute there and see what you get. What you will be getting is that Sherwood is nothing but 1 over I times root over tau. So, this is the expression you will be getting at the end of it. Now, in this expression, so in a sense, Sherwood number will be a function of two things that is observed here. One is time, another is, if you remember, in the integration of I, there is a value, that is a constant a, and a is nothing but Pw times root over tau. So, this will be function of Pw as well. So, the porosity, the permeate flux, okay, this permeate flux will occur because of the porous membrane present at the wall. So, porosity of wall will be taken care by this parameter Pw, and the time variation is taken care by the non-dimensional quantity tau. So, therefore, Sherwood will be, and if you look into Sherwood will be a function of both permeation as well as the time of operation, and as it is evident from this expression, the Sherwood is inversely proportional to time. That means, as time progresses, the mass transfer coefficient, the Sherwood number will go on decreasing. That means, mass transfer coefficient will go on decreasing, because mass transfer coefficient is directly proportional to Sherwood number. There is a non-dimensional version of mass transfer coefficient. So, therefore, as time progresses, the concentration boundary layer develops on the membrane surface. It offers, physically it means it offers more resistance against the solvent flux, and the permeate flux and the mass transfer, amount of mass transfer will be reduced. Since the amount of mass transfer will be reduced by the mass transfer coefficient, and the permeate flux will be connected by the boundary condition at y equal to 0, if you remember. So, therefore, the permeate flux will also decrease as time progresses. So, this may be of interest to the chemical engineers to design efficiently a system. Okay. So, that goes the modeling part and calculation part of the osmotic pressure controlled unstart batch cell. So, let us try to summarize whatever we have done till now. We have discussed osmotic pressure controlled filtration. Okay. So, we have discussed one dimensional modeling, we have discussed the shortcoming of one dimensional models, then we discussed the two dimensional model, In both geometries, a rectangular cross flow cell, that is a steady state process, and in a batch cell, that is an unsteady state process. So, both steady state and transient operations we have seen the modeling, how to model the system. Now, let us discuss when this osmotic pressure control filtration becomes very important. The osmotic pressure controlled filtration becomes very important when you are talking about filtration of solutes which will be having very high osmotic pressure. Okay. Solutes of low molecular weight. Solutes will not be having the osmotic pressure, the solution will be having the osmotic pressure, but the solvent must be containing the solutes of low molecular weight, because if you look into the definition of osmotic pressure, the first coefficient is RTC by m. So, if you go for lower molecular weight solutes, lower molecular weight typically you can correlate with the size, that you can talk about the smaller sized particles. If you have solutes of smaller molecular weight less, the osmotic pressure becomes dominant. Okay. For example, salt, NaCl, its molecular weight is 58.5, okay. Sucrose 342, dextrose 92, I guess, okay, 92 or 42 or something like that. Okay. So, you will be having, if you have the osmotic pressure in the range of around the molecular weight in the range of 1000, the osmotic pressure can be very important for the charge neutral solutes. For the charged proteins which will be having a high molecular weight, for example 70,000, 80,000, but because of the charge effect and other interactions, the osmotic pressure can be very high. Okay. So, if you are talking of uncharged solutes, for example polysaccharides, dextran and things like that of very high molecular weight, the osmotic pressure, the denominator becomes very large. In that case, osmotic pressure will be negligible. For most of the cases of reverse osmosis, nanofiltration and ultrafiltration of proteins and solutes having molecular weight less than 20,000, the osmotic pressure model becomes very important. Okay. It can be even for the protein bovine serum albumin, which will be having a molecular weight 70,000, the osmotic pressure is very important because of the charge effect and the other effects. So, we talk about the osmotic pressure model in those cases. So, if you remember, starting from microfiltration to reverse osmosis, most of the operating conditions of the membrane separations, they remain under the osmotic pressure controlled regime. Okay. Now, for the solutes which have a very high molecular weight, the osmotic pressure becomes negligible. Another filtration regime will set in. That is known as the gel filtration or gel layer control filtration. Okay. Now, this gel filtration is what is gel filtration? Gel filtration can occur. Now, before going into the gel layer filtration, we can discuss the various aspects of osmotic pressure model that we have already discussed. That we have seen the various osmotic pressure models for and we have identified that the mass transfer outside the membrane, that means within the mass transfer boundary layer, that has to be coupled or hooked up by the mass transfer or the solute transport or solvent transport within the porous membrane. And mass transfer outside boundary layer, outside membrane is solved by fluid flow plus mass transfer within concentration boundary layer. That has to be coupled by the transport laws within porous membrane, and these transport laws are typically the solute flux equation and solvent flux equation. Now, this solvent flux is typically and generally and for all the cases is calculated by or quantified by Darcy's law. On the other hand, the solute flux is given by either a definition of real retention or by the solution diffusion model or Kedem-Kechalski model, modified models. Okay. Either the definition of real retention or solution diffusion model that we have already discussed, and modified version of the solution diffusion model, that is the Kedem-Kechalski model. These are the various models that we have talked about the solute flux. So, by getting some definition, the appropriate definition of the solute flux and solvent flux, these two have to be coupled, and you can get the system performance prediction. And the typical feature is you will be getting a trial and error solution. The solution is always trial and error. Okay. Now, if we let us go to the gel layer control filtration, because it is another regime in the whole filtration system. It is more rampant in case of microfiltration and in at the upper range of ultrafiltration cases where the pore sizes are much bigger. Now, there are two ways when gel layer filtration can occur. In case number 1, if you talk about any osmotic pressure controlled model, basically you are talking about filtration of lower molecular weight solutes. So, initially, that means if you are talking about a batch cell operation or transient operation, initially the filtration is osmotic pressure controlled. If you talk about a steady state case, for initial length of the channel, the filtration is osmotic pressure controlled. Now, as time progresses or the length of channel it goes on, if you go as you go downstream of the channel, the membrane surface concentration increases. That means Cm is a function of tau or t or time of operation in case of batch experiment, and Cm is a function of x in case of steady state operation, where x is the length of the module. Okay. Now, and in both the cases we have seen that the minimum value of membrane surface concentration is C naught, and it will be always increasing beyond C naught, and it keeps on increasing. Now, if you plot Cm versus t or x, the curve will be typically something like this, okay, starting from C naught to let us say 5 times C naught or whatever. Now, what happens if you talking about such a system which is basically an osmotic pressure control initially, the membrane surface concentration increases with time for a batch system or as a function increases with respect to x in a steady state cross flow system, and it may happen at that particular temperature it exceeds the solubility limit. If it exceeds the solubility limit, at that point onwards the whole system, the solute particles will be deposited as a solid particles over the membrane surface, because the phase transformation will occur. Okay. So, there may be a phase change takes place. That means you are exceeding the solubility limit. In that case, the formation of solid particles will lead to formation of a porous network of solid particles over the membrane surface, that is known as the gel layer. Okay. Okay. So, that leads to the formation of the gel layer, but since it is porous, you can still expect some amount of flux, solvent flux out of it, some amount of J out of it, but that will be typically lower, and in this case we would like to avoid the gel layer formation, right. The second way of, so that is one way of formation of gel layer, and most common one is that for some solutes it is not osmotic pressure from the very beginning. In that case, we are talking about solutes of very high molecular weight. Okay. If you are talking about filtration of solutes of very high molecular weight, for example, polyvinyl alcohol, which will be having a molecular weight around 50,000 or above, pectin. Okay. Pectin is a polysaccharide. It is basically a it will be having, it is a polydispersed material, that means it will be having a molecular weight distribution, let us say from 40,000 to 1.2 lakh. Okay. It is a polydispersed. Now, things like the solutes like polyvinyl alcohol, pectin, they are well known gelling agent. Pectin is polyvinyl alcohol is a polymer, pectin is basically a polysaccharide that is available in any fruit juice, and you would like to remove pectin from a citrus fruit juice, because pectin forms an agglomeration or complex with protein and it destroys the fruit juice. Okay. So, one has to remove the pectin from the fruit juice for a clarified juice which will be having a high shelf life. Okay. So, maybe ultrafiltration can be used for it. So, if you are talking about the solutes like polyvinyl alcohol or pectin or things like that, which are well known gelling agent, the gel formation occurs from the very beginning of the filtration. Gel formation starts from the very beginning. Of filtration. So, there is nothing like osmotic pressure control and then the regime changes over to gel layer. The gel formation starts from the very beginning of filtration, and you cannot avoid that. Okay. What you can do, you can so I said in the earlier mechanism, we said that you can avoid the gel layer formation. So, you can set your operating conditions such that that formation can be avoided, but in this case gel layer formation cannot be avoided, because but the operation has to be done, because the juice has to be clarified. Okay. So, therefore, one has to be very careful and set the tuning parameters or the operating parameters such that the gel layer formation becomes minimum. And what is the definition of a gel here? It is not a solid layer, it is basically highly viscous liquid layer. I should not say liquid, it is a highly viscous fluid layer. It flows, still it flows, highly viscous fluid layer of solutes. Again, it is porous, it forms over the membrane surface, and it is gel in, we term it a gel in this particular case. Okay. So, in that I stop here. In the next class, what we will do, we will look into the modeling and the calculation of the gel layer control filtration. Okay. Thank you.